today's focus has a few more angle identities, and we're going to prove a sum and difference identity and see how to use those. So first, these are all in your book. These are negative angle identities. So what if the angle that they've written inside of the function has a negative sign in front of it? It doesn't necessarily mean you can just flip it to a negative outside. You know, this one in a function that we're graphing would be like a reflection over the y-axis, where this is like a reflection over the x-axis. So this is kind of stating whether or not those are the same thing. When you think about sine, okay, if I plot a point up here, that's a positive angle. If I do the same angle in the other direction as the negative angle, notice that these ones have a positive sine value and these ones have a negative. If your angle went further, like all the way over to here, then when you plotted the opposite, it would go all the way over here. And now this one would have a negative sine value, this one would have a positive. So the angles have opposite sine values. So that's what this is saying here. If you use the negative angle instead of the positive one, you're going to get the opposite value of the sine. When you look at cosine in that same situation, if this is my positive angle and this is the negative version of that angle, notice that because cosine is the x-coordinate, these would both have the exact same x-coordinate. This would have a positive x and so would this. So notice that when the angle is negative for cosine, it doesn't make any difference to the cosine function. It's the same as what it was before. And then tangent, because it's sine divided by the cosine, you see that it ends up following the same rules as the sine. So that just means when you see a negative angle inside there, depending on the function, if it's sine or tangent, you can rewrite it with a positive angle but a negative in front. If it's cosine, the negative angle doesn't even affect it, and you can just rewrite it with a positive angle. All right, now we're going to use this picture. It's a little bit confusing to help us with our sum and difference formulas. So just to show you where they came from, I'm going to go through it a little quick because it's a little bit it's proofy. Okay, so this big blue angle we're going to call alpha. Okay, so we're going to use these Greek letters. Again, they just stand for the angle. This little angle here I'm calling beta. And then that means there's a section in here, this part right here, which is alpha minus beta, because alpha was the big angle. Think about geometry. If I gave you this angle and says it's 80 degrees, and then I split it up and say, well, this little part of it right here is 30 degrees. What is this other part over here? You would know that it's 50 degrees because you'd do 80 minus 30. So that's kind of what's being represented in our picture. The way that our unit circle works, we label points with x and y values. However, we also said x is like cosine. So if I land on this point right here that has an x and a y coordinate, but I know that that point is associated with angle beta, the x-coordinate is the cosine of that angle, and the y-coordinate is the sine of that angle. That means if I did that exact same thing at this other position right here, this blue angle was alpha, so the x-y coordinates there would be cosine of alpha, sine of alpha. So still cosine always for x and sine for y, but as the angle varies, the answer varies, so it's a cosine of an angle. So what we're going to do to prove to you one version of this formula, and we're going to use that one proof and call it enough to say that we can do the others, is we're going to look at how far apart these 2 points are right here. Okay. We're going to call it D, and there's actually 2 ways to calculate how far apart those 2 points are. One way is the distance formula that you guys know from Algebra 1. So method number 1 is to use the distance formula and say, you know what, you can calculate that distance, or its square, by doing the x-coordinates difference squared plus the y, it's kind of like Pythagorean theorem, plus the y-coordinates difference squared. Okay, that's one way to do it. Okay, and I can dig through and I can multiply some stuff out and see how this simplifies. This is going to look a little bit ugly here. Remember, I'm squaring it like a polynomial. You can't just square bits and pieces of it. You would have to write it all out and multiply it out. So these three terms came from this part being squared. Now I'm going to work on, I'm sorry, this should say sine, you guys, because I was doing the y coordinates and it was the difference of the y coordinates. I really apologize. So let me say that again. So this was different of the x coordinates and then difference of the y coordinates. Now when I multiply out the sine values or the y coordinates and do the proper squaring there, I would get something that looks like this. And notice that I have these middle terms and these sine squared and cosine squared terms. But remember our identity. If you can do sine squared of an angle plus cosine of a squared of an angle, it adds up to 1. So what I'm seeing here is like this plus this. They're both positive, so when added together, those would make 1. And cosine squared beta plus sine squared beta would also make 1. So what I really have here is 2, because I'm counting 1 for each of those sine squareds plus cosine squareds. Then I have this term, and then I have this other term. So that's what I get for one calculation of the distance squared. There is another way to calculate what that distance is, and that is to think about this as a triangle. And some of you didn't get that extra lesson, but there is a law called law of cosines, and it calculates a side of a triangle based on the other two sides in the angle. So it's going to act like D is the side of a triangle, and the law of cosine says that that side of the triangle is equal to the side squared. Now you might think we don't know what that is, but this is the unit circle, so we're going to call that 1. So the one side squared plus the other side squared, which is also a radius of the circle, so it would be 1, minus 2 times each of those side lengths, so again 1, and the cosine of the angle that's between those two sides. So in this triangle, the angle between the two radiuses of the circle is this angle right here, and we called that alpha minus beta. So it's a weird angle because I wrote it as a subtraction problem, but that is the measurement of the angle. So as I simplify this, here's what I get. And so that can simplify completely to say that the distance squared would be 2 minus 2 times the cosine of this weird looking angle. Now, both of these things that I've written in blue are different ways to calculate the same thing, d squared. So remember how our systems of equation works? If this is equal to d squared and this is equal to d squared, then I can set those two things equal to each other. So I can set 2 minus all this stuff. So I'm just copying my distance squared calculation from one of the problems and setting it equal to the other. And now I'm going to simplify. So for example, I can subtract 2 from both sides, which will cancel out these values of 2, those terms. So then I have negative 2. I'm just going to copy this again so we can see it clearly. And now I'm going to divide by negative 2 because they all seem to have that negative 2. So I'm going to divide this side by negative 2 and this side. So on this side, that's canceled. On this side, remember this negative 2 needs to be a denominator for both these terms, so it cancels out this negative 2 as well as this one. And I end up with cosine alpha cosine beta minus sine alpha sine beta. So this is actually one version of the difference formula. So we're not going to do this over and over again, but we're just going to list them for you. So for our sum and difference formulas, there's different formulas for sine, cosine, or tangent. So for the sine formula, I want to talk about some notation right here. I'm doing two formulas in one. What if it's a plus versus what if it's a minus? And what I'm going to show you is that the sine formula looks like this. And I'm going to explain how to use the signs properly. So in other words, if it's a plus, then this one's also a plus, okay? If I wrote this on top, then I use the sign that's on top. So instead of me having to write out the formula twice, this is a way that mathematicians often write it, and you can get used to that notation. For the cosine formula, it just looks slightly different. We just found one of these. So notice here that in cosine, if it's a plus, then in my formula I'm using a minus because those were the ones on top. And then the formula for tangent will look like this. So it has tangent of alpha, matching signs first, and then it has a denominator where they use the opposite sign depending on what's happening in the problem. All right, so those are our three formulas. Pause it if you have to get them down, and then we're going to work on using these either to help us again in proofs or to be able to do some calculations that we might not be able to do otherwise. So here are some cofunction identities, okay? Probably the most important one to learn out of here is this one, if you're going to memorize one. The other ones you can derive, and what I mean by that is I'm going to answer this, can you show these are true questions just with this. Notice I'm working with sine and it says pi over 2 minus theta. Let's use our sum or difference formula. So my sum or difference formula, this is like my alpha, this is like my beta, and it's a sign with a minus in between it. If I follow the steps of the formula, here's the sign, the alpha and the beta. This one had a minus sign, so I'm going to put a minus sign in my formula. And if you follow through that formula, it says that this would be equal to sine of the alpha angle times cosine of the beta angle with a minus side according to our formula, and then cosine of the alpha angle, sine of the beta angle. You might think that that looks nothing like this, but let's simplify. So the sine of pi over 2 is 1. That's something we can actually calculate from our unit circle. The cosine of pi over 2 is 0. 1 times cosine is cosine, and 0 times sine is 0. And so this just simplifies to be cosine of theta. So that's how all of these were determined, but you don't really see this one as well, the cotangent. You get some undefined values, so this is one that you'd want to have memorized, or in our case written down, since we're letting you use the formulas on the exam. So how can this help us figure some things out? So notice example 1 asks me to find the exact value, that means leave radicals and all that stuff, of sine of 105. And 105 is not a special angle. It's not a 30, a 60, a 45. However, there are some ways I can make 105. One way I can make 105 is like 60 plus 45. And so I could, if I think of 105 as 60 plus 45 and split it up, the sine formula just uses the alpha angle and the beta angle, meaning it would have all things that were either calculations of a 60-degree angle or a 45, and I could figure those out. Okay, so I'm thinking of the 60 as my alpha and the 45 as my beta, and if I follow that sine formula, it says to do sine of the first angle, cosine of the second one, has the same sign between it, like this one's a plus and there's a plus, and then it has cosine of the first angle times sine of the second angle. And then these are things I can actually calculate and plug in and finish the calculation. So the sine of 60 degrees according to my unit circle, rad 3 over 2. The cosine of 45 is rad 2 over 2. The cosine of 60 is 1/2. The sine of 45 is rad 2 over 2. So I'm going to multiply each set of fractions together that can be multiplied together. So this is rad 6 over 4 and rad 2 over 4. And so my final answer here, most simplified I can get, leaving the exact value, is rad 6 plus rad 2 over 4. Now I'm going to go and look at cosine of 255. So again, I need to try and find a way to think of 255 as something that I could figure out. So I could think of it as, let's see, I know 210 and 45. I could think about it like that. Okay, can't do 240 and 15. I could do, I think that's it. I'm definitely going to need a 45 because those are the only ones I have with special. So I'm going to go with 210 and 45. I'm sure you can find another way if you wanted to. So I'm going to think of 255 as split up being 210 plus 45. And again, 210 is my first angle, my alpha, and 45 is my second angle, my beta. And now look closely at your cosine formula. It says cosine of the first angle times cosine of the second angle. But then when the formula has a plus, it has a minus on the other side of the formula. And then it does sine of the first angle times sine of the second angle. And again, I'm going to plug in the values I know and calculate them. So 210 is like 30 degrees past 180. The cosine there is negative rad 3 over 2. Oh, and I'm sorry, this should have said 45. And the cosine at 45 is rad 2 over 2. The sine at 210 is negative 1/2, and the sine at 45 is rad 2 over 2. So this is negative rad 6 over 4 minus negative rad 2 over 4. So it's a common denominator of 4, and this will be a negative rad 6. This minus a negative rad 2 will become plus rad 2. So those sum and difference formulas allow me to calculate something I wouldn't normally be able to calculate. All right, and now we're going to go through and verify each identity. So again, this is like you were doing before, you're just doing proofs. Okay. Whenever it's a sum or difference, I don't feel like there's as much of a question as there is with the Pythagorean identities. I know where to start. I always start with this and expand it out to what the formula says it could be. So I'm going to start with the cosine 90 minus theta and use my formula. And it says I would do cosine of the first angle, cosine of the second angle, plus sine of the first angle, sine of the second angle. And then I'm just not copying down the right side right now as I do my proof. The cosine at 90 is 0. The sine at 90 is 1. So this is 0 plus sine theta, and that will work out to be sine theta, which is what I was looking for it to equal on the other side. Okay. All right, so in part B, in all of these, I'm starting on the left side just because they wrote that sum or difference, this thing with two angles being added or subtracted on that side, so that's what I'm starting with. So again, I'm going to expand this using the cosine formula. So cosine of 180 times cosine of theta minus sine of 180 times sine of theta equals, and I'm just not working on the right side right now. You guys don't have to write that squiggly line. I'm just trying to make it clear to you guys that there is something over there that I'm not writing it. Cosine of 180 is 1. Negative 1, excuse me, and times cosine theta. And sine 180 is 0 times sine theta. So this will be negative cosine theta minus 0. That would be negative cosine of theta, and that's equivalent to what's on the other side of this identity. All right, and then finally part C, I'm going to work on the same thing. This time it's a sine value that I'm expanding. So according to the formula for sine, I would do sine of the first angle, cosine of the second angle. Because this is a minus with the sine identity, this is also a minus. And it would be cosine of the first angle, sine of the second angle. So as I go through and do this, sine of theta is sine theta. Cosine of pi over 2 is 0. Cosine of theta, sine of pi over 2 is 1. So this would be 0 minus cosine theta. And so that would equal negative cosine of theta, which is what I was trying to show it was equivalent to on the other side. All right, lastly, just making sure you guys recognize that sum and difference formula can be used both ways. So in every example I've done it so far, whatever's been in our problem has been something that I'm expanding, but I wanted to make sure you guys can recognize it when it's already expanded, but you can condense it. Like if I asked you to calculate this, you might look at the 50 and the 40 and be like, Ms. Dahl, that's not possible without calculator. I agree with you as far as 50 and 40 goes. However, you should recognize, because there's two trig functions multiplying together, plus or minus, and then two more trig functions, that this is something that you should recognize. So look at which trig function that has cosine times cosine and then sine times sine when we look back at our sum and difference formulas. Cosine, cosine, sine, sine. It's a cosine function that has that. So I would expect this to be a cosine, where in the parentheses I was using a 50-degree angle and a 40-degree angle. Now, this has a minus between them, but remember, it depends on which function it is, whether you're using that minus or not. I'm going to go look at that expansion again. And for the cosine, when that had a minus between them, that meant in here it was actually a plus. So this expansion is the same thing as a cosine sum formula, which means they're really just asking me for the cosine of 90, and the cosine of 90 is 0. So again, you want to be able to use your sum and difference formulas to prove things are equal, as well as do calculations. If you know those formulas and how they work, they won't be as difficult as verifying the identities with the Pythagorean ones. So your practice today might include a combination of both. So you have a skill 1 homework on the Pythagorean identities, a skill 2 homework on sum and differences, and then you have a handout that addresses both of these.